Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will discuss the cooling load and how the cooling load is represented on psychometric chart. Today in this lecture we will discuss the working of an split AC, then sensible heat factor, gross sensible heat factor, effective sensible heat factor and heat sources in the building. Now in split AC you must have observed that there is no arrangement for the fresh air in normally the ACs which are available in market, and it is very popular. I mean a preferred kind of AC nowadays because it is convenient to use, convenient to install. Now split AC is recommended for a small size of building where infiltration, it is assumed that the infiltration load is sufficient to meet the oxygen requirement. Otherwise, as there is no arrangement for fresh air, 100% recirculation of air takes place inside the split AC. We will see how load in a split AC taken into account, and we will represent that load into on a psychometric chart. Now we have assumed that outside conditions are 35 degrees centigrade DBT and 70% RH, a typical of coastal climate. So if 70% DBT and 70% RH is to be located here, then 35% DBT and 70% RH it is going to be here. That is the outdoor condition, right? And then it says the return air. Return air means after taking heat from the room, return air goes back to AC. So return air is 27% dry bulb temperature and 60% RH. So return air is 27 degrees centigrade dry bulb temperature and 60% relative humidity. Now if we consider these two states, then one is 35-70 and another is 27 and 60% RH. It is further stated that air supply to the room is 15 degrees centigrade. It means the temperature at which the air is supplied to the room is 15. So 15 degree can be located here, somewhere here on this vertical line, somewhere on this vertical line. Coil due temperature is 10 degrees. Now coil due temperature is a new word here. Coil due temperature means coil temperature. It is assumed that when the condensation over coil takes place, air becomes 100% saturated if there is no bypass of air. So it is 10 degrees centigrade. So I will draw this diagram on the board also. Now this is outdoor condition, 35 degrees centigrade, 70% RH. This is inside condition, 20 degrees centigrade dry bulb temperature and 60% relative humidity. Apparatus dew point temperature or coil dew temperature, it is also known as apparatus dew point temperature, ADP. So ADP is 10 degrees centigrade. Why it is called ADP? Because this is the temperature of coil and it is assumed that it is at this point the air is 100% saturated. So if the air moves over this coil, if there is no bypass factor, air will be 100% saturated, because air gets saturated the moment it comes here. Now after reaching at this state, the air gets saturated during sensible cooling, after sensible cooling, then dehumidification starts, cooling with dehumidification starts. So, throughout this process, let us say 1, 2, A and B. So, throughout the process A to B, the cooling of coil takes place, because you can see the dry bulb temperature keeps on reducing, dry bulb temperature keeps on reducing in this direction, and at the same time specific humidity also comes down. Specific humidity is depicted here on the y axis, it also comes down. That is why when we reach at state B, the air is 100% saturated, provided there is no bypass of air. If some bypass of air is there, so it means air will be directly mixed with the saturated air, and it will no longer remain saturated air. That is why when we join these two lines, if bypass factor is there, you will find that we will see that the air is not saturated. Anyway, so from air supply to the room is 15 degrees centigrade. So, air supply to the room is 15 degrees centigrade. So, we will draw a vertical line from 15 degrees centigrade, and where it cuts, wherever it cuts, it is the air supply to the room. Wherever it cuts, it is the air supply to the room. Now, this is point 3. So, point 3 can be located here also. This is 10 degree centigrade line, and outside air is cooled first of all initially, then air is supplied at 50 degrees centigrade from here. So, that is point 3. Now, when outside air means when we start the AC, then we assume that the room is filled with the outside air and the room condition is 35-27. After running certain time, this supply air, now it picks heat from the room. Now, this thing we did not discuss when we discuss about the psychometric processes. We always assumed that the supply is 24-50%, 24 degrees centigrade and 50% RH. But in actual practice, the air which is entering the room, because it has to pick heat from the room also, it is normally in 13 to 15 degrees centigrade, and now this air enters the room and picks the room heat from the room, and return air attains the state of, this is state 1, this is state 2, and this is state 3. Now, in this process 3 to 2, it is picking heat from the room, and now after attaining state 3 from air conditioning coil, the air is supplied to the room and the return air is at 27 degrees centigrade. Now, this air is getting recirculated. I mean, return air is coming from the room, is again entering the coil, and after entering the coil it gets cooled, and then it is again recirculated in the system. Now, process 3 to 2. Now, process 3 to 2 is important for us because it shows load of the room. It may include the load of the infiltration also. I told you in the previous lecture that infiltration load can be calculated if we know the amount of air which is getting infiltrated into the room, then how much sensible heat it is bringing to the room and how much latent heat it is bringing to the room, it is calculated, and that load also is also incorporated here. Now, this process, this 3 to 2 has two components. This is sensible heat and this is latent heat. So, in a room there are two types of heat addition, sensible heat addition and latent heat addition. And during sensible heat, for example, the heat added by the lights, heat added by the occupants, heat coming through the wall, this is all these are all components of a sensible heat addition, because there is a change in temperature during these heat additions. But some of the heat additions, there is no change in temperature or dry bulb temperature of the room. For example, suppose water is boiling in this room. So it will, boiling water definitely add some sensible heat, but it will definitely add some latent heat of the in the room, because vapors will be added into the room. Now after working of split AC, we will talk about sensible heat factor. As I told earlier that this is the room load. So if this is the room load, air entering the room at this temperature, leaving the room at this temperature, this is the sensible heat added in the room. This is latent heat added in the room. The total heat, say it is Q is equal to sensible heat plus latent heat, and sensible heat factor is equal to sensible heat divided by sensible heat plus latent heat, right? And this line, I will in next time in next psychometric chart I will show you how to draw the sensible heat factor lines. So sensible heat factor gives the idea about the nature of the load. For example, where their latent heat load is minimum, for example, a residential house, sensible heat load factor may be 0.9 or greater than 0.9. For example, in a restaurant, because a lot of cooking is there, sensible heat factor may be, let us say, 0.8. In a discotheque or a dance floor, the sensible heat factor may be 0.7. So this, the moment we keep on increasing the sensible heat factor, the slope of this line keeps on increasing. I will show you the sensible heat factor on a psychometric chart. In this chart, there are certain dash marks on this scale, and there is a half circle also. You can use either of these two. Suppose I want to have a sensible heat factor of line of 0.9. Suppose I want to have a sensible heat factor of line of 0.9 or 0.8, right. So what I will do, I will say these divisions you can see they are not uniform. Here the distance between the, say it is 0.4 and 0.3. So this is 0.01, but here if you look at the 0.01, they are very close to each other. Now I want to have a constant sensible heat factor line of 0.7. So this 0.7 I will be joining with this one, this ideal condition, and any line parallel to this line is 0.7, so it will be having the slope of 0.7. So here on a psychometric process, if I want to show the constant specific sensible heat factor line, so suppose this is our room air condition. So if I want to have sensible heat factor line of 0.8, let us say, I will pick a mark of corresponding to 0.8. I will join, suppose this is our ideal condition, 24 degrees centigrade temperature and 50% RH. So I will join this line with 0.8. And this is the sensible heat factor line. Suppose my load point is here. So what I will do, I will simply draw a line parallel to this, and this will give me the load line. Same thing I showed you in the case of a split AC. So when there is a load in the room and we transform the processes on a psychometric chart, these sensible heat factor lines are helpful, are very helpful. Now we will further discuss on this. There is a gross sensible heat factor also. There are two terms, sensible heat factor, three terms, sensible heat factor, gross sensible heat factor, and effective sensible heat factor. Now sensible heat factor we have taken from the load point. Now outdoor condition is this one, suppose, and there is a mixing, let us assume there is a mixing also. So, if there is a mixing condition is this, coil temperature is this. Now, this is gross sensible heat factor line. This is gross sensible heat factor line. As definitely the gross sensible heat factor line has higher slope than this one. So, gross sensible heat factor will be less than the sensible heat factor of the room. This is apparatus dew point temperature, and if we join this, suppose air is supplied at this temperature, then this temperature becomes room dew point temperature. Right? And this is sensible heat factor line, and there is another term which is known as effective sensible heat factor. So, effective sensible heat factor is drawn from here. So, that is the effective sensible heat factor line. So, these things will be useful when we will solve some practical problems on air conditioning load. Now, heat source in a building. Now, heat source in a building can be divided in two parts, that is sensible heat load in a building and latent heat load in a building. Now, sensible heat load in the building is that load when there is energy addition in the building, there is a temperature rise. So, there are many sources for sensible heat load, that is heat flow through walls of the room, heat flow through the ceiling, heat flow through the floors and windows, and through windows and doors there is infiltration also, and infiltration also brings the sensible heat to the room. Normally in a single storied building, maximum heat transfer to the room from outside takes place through the ceiling of the building. So, if we are able to, or anyhow if we do the roof insulation, in that case cooling load on the air conditioning system can be grossly reduced. Even if we do not do the roof insulation, if we put some sort of white reflective tiles on the roof, that will also bring down the cooling load on the air conditioning system. So, sensible heat sources are heat flow through walls, ceiling, floor and windows. Through windows, direct radiations also enter the room and these direct radiation, they heat up the articles in the room, and secondary radiations takes place, and they are long wavelength radiations and they cause heating in the room. A sort of greenhouse effect is created in the room. Solar radiations, they fall on the building and then the part of the radiation is absorbed and that is subsequently transmitted to the building, to the transmitted inside the room. There is a load from the occupants also. So, each individual, if individual is sitting idle, in that case he or she shall add 100 watts of sensible heat and 90 watts. 90 watts of sensible heat and 30 watts of latent heat. Approximately we assume that each individual adds around 100 watts of heat. So, if this room is occupied by 100 persons, together they will be adding 10 kilowatts of more than 10 kilowatts of heat, and the cooling load by the occupants itself is going to be more than 3 tons because 10 kilowatts divided by 3.5 and it is going to be more than 10 tons. So, approximately 3 tons of cooling load will be due to occupants only. There are different equipments, even UPS, laptop, desktop, they also emit, they are also heat source in a room. And food products, whether they are cooked into the room or they are brought into the room, they also add heat to the room. In the cold storage, when we design system for cold storage is the air change rate is very low, maybe 1 air change or 2 air changes per hour, but the heat liberated by the food products is high. and this high heat liberation from the food products has to be taken away by the cold air coming from the air conditioning plant, and per kg of food product, I mean the heat in the form of, let us say, 600 or 800 kilojoules of heat. I mean there is a huge list for different food products. There is a different value for heat liberated by the food products. Infiltration I have already discussed. Now latent heat sources are cooking occupants and infiltration. This I have also discussed. In addition to this, other equipments in the room, like some UPS is lying in the room. So UPS is also adding heat, even light, tube lights. Each tube light is approximately, in old tube lights, the choke was of 60 watts. Nowadays we have new chokes which consume only 40 watts. This 60 watt choke was earlier, 60 watt choke was used for, this is for information, 60 watt choke was used for 40 watt tube lights. But nowadays we have improved chokes, they consume only 40 watt for 40 watt tube lights. So each tube light contributes 40 watts of heating. So if there are 10 tube lights in a room, then again the heat addition is going to be 40 watts, 400 watts. So this way we can find out, I mean when we do the load calculation, all these aspects are taken into account, and finally sensible heat and latent heat in a room are calculated. Sensible heat factor is calculated, and sensible heat factor line is drawn on the psychometric diagram, and the designing of the system is initiated. All these issues we will discuss in the subsequent lecture, because it is also on the cooling load. This is all for today. Thank you very much.